Our next speaker is Milijana.
Thank you. So yes, my name is Milijana Surbatovich, and I'm going to be talking about my work entitled IO-Dependent Idempotence Bugs in Intermittent Systems, which I did together with my advisors Limin and Lucia. This work looks at a new class of bugs caused by input that are endemic to energy harvesting devices. Energy harvesting devices are an emerging platform of batteryless devices that enable computing in inaccessible environments. They do this because batteries can be expensive or even impossible to access and replace in environments such as remote wildlife monitoring or space satellites, or maintenance can just be highly intrusive, such as in in-body implants. Instead of a battery, these devices are equipped with an energy buffer, which is implemented with a capacitor, and a harvester, such as in this case a solar panel, that gathers energy from the environment as it is available. The device will be off until the buffer charges, at which point it turns on and begins to compute, sense, and communicate. It will remain on until the energy buffer is depleted, which can happen if the device is simply using more energy that can be harvested, or if access to the energy source is removed, such as if a cloud goes in front of the sun. At this point, the buffer will empty and the device will turn off at whatever arbitrary program location it is. Once the device turns off, any volatile state clears, which typically includes the program counter and registers, whereas persistent state remains. The device will remain off until the energy buffer refills, at which point it will turn on and begin to compute again. So this intermittent operational cycle will cause bugs without system support. For starts, since the program counter clears when the power fails, the system will need to save the volatile state periodically to make meaningful progress through the programs. So then, as the program executes until the buffer empties and the power fails, when the device reboots, it will begin from the last checkpoint and re-execute the block of code in which it failed. Because of this, any re-execution must be idempotent. In other words, many re-executions of a section should result in the same final state as one continuously powered execution. And why might execution not be idempotent? Consider if B has what's called a write after read dependence. So X gets the value of Y, and then Y is overwritten to 5. So this has no data flow. But if Y is in persistent memory and block B re-executes, then this re-execution introduces data flow from the assignment of 5 to the assignment into X. So in order for programs to complete correctly, the system also needs to back up the original value of any variables that have a write after read dependence, along with the volatile state. And now current systems have done this. They provide forward progress and fix write after read bugs, but is this enough for programs to execute correctly? Now the question that we ask, and that hasn't been addressed in prior literature, is what about input operations? Consider if block B gets value from a sensor. On re-execution, this could potentially result in a different value being assigned to X. And we find that yes, current system missed bugs caused by repeated input operations. And this is a problem because we want to port existing code bases to our energy harvesting devices, but prior systems only address progress and write after read bugs, so they're not going to port programs correctly. For the rest of my talk, I'm first going to discuss why repeated I/O operations can cause idempotence bugs. I'll describe our bug detection tool, IBIS, and finally I'll describe our evaluation and conclude. So repeated I/O reads can cause idempotence bugs. Consider this example program. It gets the temperature from a sensor. It checks if that input was below a limit, setting the steady flag. If it was, otherwise setting the blink flag, and assume these variables are initialized to 0 in non-volatile memory. And then it asserts that blink and steady can't both be set at once because these are on mutually exclusive paths in the program. So what can happen when running intermittently? Let's say our environment starts out as being cold. So on execution, the temperature will be cold, the input will be below the limit, and the program will set the steady flag in non-volatile memory, at which point the power fails and the device turns off. While the device is off, some accident happens in the environment. So when the device reboots and starts to re-execute, the temperature will now be hot. So the input value is different and it's now above the limit, and the program will send the blink flag in non-volatile memory, and now the assert will fail because both flags are set. So the problem here is that this control dependence on input caused inconsistent updates because the program took one path, set variables in persistent memory, and then on re-execution, it took another path, setting different variables in memory. And now, since prior systems back up write after read bugs, they won't catch this because steady and blink are write only. There is no write after read dependence. And now, if repeated I/O reads cause bugs, the very simple fix is just prevent I/O from repeating. So the programmer could place a checkpoint between the sensing and processing of that input. However, as is pointed out in the prior work Mayfly, this can break what's called program timeliness, the idea that data should be used within a certain window, otherwise it should be regathered. And I'll go through the example once more to show why. So to start, the environment is cold. As before, the temperature is going to be below the limit, the steady flag will be set in memory, and the device turns off, during which the accident happens. And now the device will be off for an arbitrarily long period of time until the buffer recharges. But once the device reboots, it is not going to regather the input. So the input is still going to be cold, it's going to evaluate to below the limit, and it's going to consistently set that steady flag in memory, but this is the wrong outcome because it's no longer matching the actual state of the world. And so the device is going to fail to send out any warnings based on the fact that the accident has happened. So to recap, this is why detecting input bugs is particularly important for energy harvesting devices. These are sensor-driven platforms that are frequently processing inputs. Repeating the input can cause bugs, but not repeating it will actually break the program behavior. So we characterize input-dependent bugs for the first time and develop tools to detect them. And that's what I'm going to describe next. We make two variants, IBIS static, which is less precise, but it has full code coverage at no runtime costs, and IBIS dynamic, which has no false positives, but it may practically have less coverage and obviously incurs a runtime cost. So the goal of IBIS-S is that it uses a fairly off-the-shelf Tate analysis to analyze the reach of inputs, and then it checks those input tainted instructions for the characteristic bug pattern and reports any instances to the programmer. So the goal of the Tate analysis is to track data flow, both direct and indirect, off of inputs. We implemented this in the LLVM compiler infrastructure. To start, the programmer must annotate the name of any function that can produce non-idempotent input. The algorithm then marks uses of annotated functions as tainted and adds them to the work list. So in our example program, that would be input. Next, the algorithm gets an item from the list and propagates taint to any uses, which in our example is the branch. Since we are tracking indirect taint as well, as the third step, if a branch is tainted, taint propagates to any dependent stores, which in our program is steady and blink. And now this process repeats until the list is empty, so steady has no more uses, whereas blink has one, which then leaves the current function. There are several ways that taint can flow into procedurally. In our example program, it was through a function argument, so taint propagates from the use in the caller to the use in the callee. Other sources that we covered in the paper are global variables, return statements, and pass by reference parameters. To continue with our example, taint flows from blink to val, directly to the branch on val, and then indirectly to the store to events. So this concludes analyzing the reach of taint off of the original input. Now the pass is going to check for the characteristic bug pattern. Now we identified this pattern and formalized it in the paper. Simply stated, it's a pattern where a tainted branch has paths that write to different variables. And this is buggy because if on the first execution, program writes to blink, and on the second re-execution writes to steady, that old value of blink is still going to be in memory and inconsistent with the current input value. On the other hand, if both sides write to the same set of variables, blink and steady on the first execution, then on re-execution, both blink and steady will be overwritten with fresh, consistent values. So the pass examines the tainted instructions for occurrences of this pattern, and then outputs the tainted branch and the differing variables written to the programmer. Now, we also implemented a dynamic tool, which is still a development phase bug detection tool, not a deployment phase runtime monitor. Though the conceptual criteria that it looks for is much the same as the static tool, the engineering is necessarily rather different. So IBIS-D, in short, dynamically tracks taint and freshness. Like any other taint tracking tool, taint asks whether a variable is input dependent, but new to our system, we also track freshness, which asks whether a value is written on the current execution. Because the correctness criteria that IBIS-D upholds is that an execution must not read a stale tainted value. This is because this corresponds to the program writing input-dependent variables and then on re-execution taking a different path and not overwriting those input-dependent variables. So I'm going to give a brief illustrative code snippet. So say y gets some input, z gets that value of y, and w gets some value of x, where x is tainted and not fresh because on reboot and re-execution, nothing's fresh. So on the assignment to y will get marked as tainted because it got the input, and fresh. Z getting the value of y will propagate the taint and the freshness, and y getting the value of x will generate a runtime warning because x was stale but tainted. So I don't have enough time to go into the implementation details of IBIS-D, but there's two main components: a shadow memory to record the metadata, so that's the 2 bits, taint and freshness, for each byte, and a compiler pass that instruments the program with calls to the runtime library that manipulates this metadata. Now that I described the tools, I'll discuss how we evaluated them. So the high-level goal of the evaluation for IBIS-S is whether it provides usable reports to the programmer. So yes, it reports bugs with not that many false positives. And for IBIS-D, we wanted to see if it had reasonable runtime and memory overheads. There is no standard benchmark suite for intermittent computing, so we assembled a collection of existing intermittent apps from the prior literature, as well as embedded system drivers, since one of our use cases is to see whether our tool will help with porting embedded system code to energy harvesting devices. We then ran IBIS-S on the benchmarks, first manually categorized the results as true or false positives because there is no ground truth, and then performed software validation on any of the reports we consider true bugs, the details of which are in the paper. And we find that IBIS-S does find bugs with few false positives. So this graph on the y-axis is the number of reports. On the x-axis is the name of the benchmark. Benchmarks to your left are the existing embedded system apps, and benchmarks to your right of the dotted line are the apps from prior literature. Green bars denote true bug reports. Yellow and orange denote false positive reports. We categorized the false positives into 2 categories: no bug, where the report simply did not correspond to a failing execution, and no use, where it matched the tainted pattern, but there was no use of the tainted data after the paths rejoined. And a blank bar just means there were no reports generated. It's not an error in our plotting software. So you can see that the sensor drivers were likely to have bugs, and the full applications were not driven, so they didn't have bugs, but nor did we report false positives for them. Since we evaluated IBIS-D on an actual energy harvesting platform, we needed the apps to be runnable. So for the existing embedded system drivers, we first took functions that IBIS-S reported as having a bug, turned that limited set of functions into a runnable app, and then ran the extracted applications and the intermittent applications with IBIS-D instrumentation and unaltered, and then we compared those runtimes. So here's a graph of the results. The y-axis is the slowdown, and the x-axis is, as before, the name of the apps. And the slowdown is the instrumented runtime normalized to the continuous runtime. So we found that IBIS-D had 25 times mean slowdown against unaltered, which is in line with a memory checking tool such as Valgrind, so reasonable for a bug detection tool. And there was the constant shadow memory overhead of 2 bits per byte. Now that I've described our evaluation, I'm going to discuss the comparison and limitations of IBIS-S and IBIS-D. Because we use a pretty standard Tate analysis, IBIS-S is not going to be sound. It has false positives, mainly due to opaque path conditions and computing the may-write set off of any tainted branches. And while it can cover the entire code base, it might not find all the bugs because alias imprecision could technically cause it to miss a tainted flow. On the other hand, IBIS-D is sound because we do detect only concrete bug instances while the device is running. And it is complete if and only if all paths are explored, which is difficult for intermittent systems for reasons I'll explain on the next slide. Our implementation and design of IBIS-D uncovered a few interesting challenges. One is implementing something like symbolic execution for intermittent systems, because these idempotence bugs don't manifest just on exploring one code path. So exploring all code paths isn't enough to find them, because these bugs only manifest if the device fails, reboots, and re-executes. So it's the path, the power failure point, which is arbitrary, the restart point, and then the re-executed path is where the bugs will manifest. So finding a rigorous and efficient way to explore this space is an unsolved challenge. Additionally, another unsolved challenge is safe instrumentation. For a program to be able to finish executing, each code block between checkpoints needs to finish in one energy buffer. However, instrumentation necessarily adds code to the block, so a safe program instrumented could be unsafe and never finished. So finding a way to verify that a program transformation of an energy safe program results in a program that is still energy safe is also unsolved. You can read many more details in the paper, including a discussion of how IBIS-S integrates with differing intermittent execution models, more details on the implementation and evaluation for both systems, as well as a case studies of a selection of bugs that we found. To summarize, we characterize I/O idempotence bugs for the first time, as they are not addressed by prior systems. We find that they exist in real code. We developed our static tool, IBIS-S, and it provides information to programmers about these hard-to-reason-about I/O dependencies. And we developed a dynamic tool, IBIS-D, that detects concrete bug instances when running on real energy harvesting hardware. Please read our paper, and thank you for listening.
All right, we have time for questions while the next speaker sets up.
Okay, so you said that the system would be correct if there was no alias problems. So if there are, so you said that that was one of the problems, but are there other problems than the aliasing, or?
Yeah, so it's not complete because of alias, because it could miss taint flows. Yeah, so opaque path conditions could cause it to incorrectly report something as a bug. If just looking at the write sets, it seems like they could be different on each side, but because of the actual condition, they'll end up always being the same write set on both sides, so we'd report that, but in actuality, it's not a bug, right?
Yes.
Yeah.
Okay. Good.
Yeah.
Right. Okay. If there are no other questions, then let's thank Milijana.